Yes, so I'd like to thank the organizers for allowing me to invite myself here for a few days. It's a very nice place and very nice program too. So what I'll talk about may have some relevance to geometric Langlands in the TQFT perspective, if it ever works as a general theory as opposed to a low-dimensional example. So what I'll talk about is, I'll try to explain what it means for groups to act on categories and a bit on two categories, and how one could use that to construct gauge topological quantum field theories. So presumably, the geometric Langlands theory that Kapustin and Witten talked about comes from a Lie group action on a 3 category, which is likely to be either the trivial 3 category or some easy variation on that. Now, as we'll see already in low-dimensional examples, there are several things one can mean by group action categories, even lower dimensions, so the possibilities multiply a bit, even if you want to gauge something like a trivial theory. So what's a background? So I should mention, as a motivating background, so relation of DQFTs, I'll mention the Koboris hypothesis, which was it's a theorem now. It was proved by Jacob Lurie, and the idea, I think, was quite old. It was formulated in some manner by Baez and Dolan some time ago. The idea is that if you have a TQFT, which in Atiyah and Witten, Atiyah, Siegel and Witten. So let's say we're talking about n-dimensional. And Atiyah, Siegel and Witten meant that to enclose n manifolds, so maybe I should say it that way. So just a functor from the Bordis category, Bord, let's call n minus 1 n, onto vect and tensor, this disjoint union. So this is a category of the objects are closed n manifolds, and the n minus 1 solid manifolds, and the morphisms are n-dimensional Bordisms. That was the original definition of a TQFT. And the idea, going back to at least to Baez and Dolan probably before that, is that in fact you could extend the structure all the way down in codimension to points, and these kind of things might be easier to classify. And that's indeed what was proved. So the theorem says that if you have a functors from the 0 through n-dimensional Bordis category, but with a little twist or a lack of a twist, for framed manifolds into some n category, I'm not going to define that sort of thing here, then it suffices to specify where the point goes. And the acceptable object, so the theorem is the image of a point defines the theory, defines a functor, determines a functor. So maybe theorem 1. Theorem 2, which I won't state, that the constraints on the possible images are known on, let's say, this is a functor z of a point. Constraints on this are known. And 3, if you want the original notion of TQFTs, which allows manifold to structure, like maybe just orientation or some structure of a tangent bundle, is functors from G Bordis category, where G is some structure on the tangent bundle, so it's a group mapping to them, correspond to G fixed point set inside the set of possible objects. Points in the acceptable object, or inside all frame theories. So somehow in addition to the explicit description, the content of the theorem is that if you want framed manifolds, there are only constraints, and the data comes in when you asked to extend to manifolds the structure on the tangent bundle. Acceptable objects, yes, thank you. Acceptable targets of these are called fully dualizable objects. So constraint no definition are called fully dualizable objects. They're not easy to describe, the constraints, but they are known. So let's just say fully dualizable. All right. Where are we? For n equals 2, that's right. It was known in several special cases were known. Going back to Kontevich, Zoibelman, Costello, and other people who worked in string topology, so with various degrees of generality. This had been done in 2 dimensions. Actually, I shouldn't say that. The oriented version was done in 2 dimensions. The framed version in 2 dimensions was that already was new. For the oriented version, it looks like this data to be specified. So if you take the 2 category of linear categories, you need a Frobenius structure on the linear category to define the theory, but that's only because you're asking for oriented theories. So the data is an illusion. Well, not an illusion, but it comes from, it sort of coupled the tangent bundle. All right.
The stable version was done in all dimensions, right?
What do you mean by the stable? Oh, if you... There is a version of, well... No, I'm not sure to answer that well, but there is a connection here with the Madsen-Weiss theorem in all dimensions, that's right. But that classifies very, very special TQFTs. Essentially, for those TQFTs, every vector space associated with a closed manifold has to be a line. Those are the only acceptable ones. Units, yes. The units in the category of TQFTs were classified by the Madsen-Weiss theorem in every dimension. That's correct. That's right. But armed with that, we can try. I mean, if you have the question now, it's given a TQFT, and let's say G acts by symmetries, which has to be defined. Can we gauge it? And I think before we had some classification theorem, it seemed a bit difficult to even begin to ask the question, because, I mean, nothing here is very clearly defined. But I think with the theorem now, we can ask that question. So, for example, how many, let's try to classify all the pure gauge theories given with finite group G. Pure gauge theories mean gauged versions of a trivial theory. So we'll see in a second there's more than one such thing. So basically, I mean, the idea which comes from physics, but we only knew how to do something with that dimension n-1 before, was, well, saying that you can act by symmetry on TQFT meant that you can couple the functor to manifolds, principal bundles, and then the quantum theory you want is integrating over all principal bundles. Now, integration could mean a path integral as integrating some function, or it could happen in topology or integrate homology classes on the modular of bundles. So in principle, so the gauging procedure, gauging has 2 steps. So you promote the theory to a classical gauge theory, where domain is the category of manifolds with principal bundles, plus G bundles, let's say. You may ask for the bundles to be flat, depends on the context or not. And then the quantum gauge theory integrates over bundles. So what's assigned to a manifold is, well, you take what's assigned to a manifold with all possible G bundles on it and integrate over the G bundles, and you get back to a theory on manifolds, possibly with structure of a tangent bundle. And in fact, that theorem tells us, contains in it what it means to form the classically gauged theory. Because you can take your favorite Lie group G and map it to ON by a trivial map that's allowed. The category you get will be framed manifolds with G bundles on them. Or if you like oriented manifolds, you can take the group G cross O cross SON, say, and map it to ON just by projecting out G first. And then you get the category of oriented manifolds with principal G bundles. So that's already contained in there. And the theorem says in that case that what you need to have described an action of G on Z of a point, and that just to be able to classically gauge the theory, and then the classically gauged theory, actually, sorry, that's, and that I'm sorry, I think I need to back up in my mind 1 second. I think for classically gauged theory, have that input, that makes an action of G on this thing is a way of making the point G invariant in the ambient category. And what you need to, at the end of the day, if you want to quantize, you must produce just sort of one object functor from the Borist category without G bundles, so it must be generated by something. And that something, if you believe in physics, should be, well, it's associated to the point. The point is a single principal G bundle, the trivial bundle, but it has, of course, lots of automorphisms. So you're living over BG really now, the gauged category. So you want to take the path integral over BG. That's what we would like to assign to a point, the quantized theory. So the quantum theory, sorry, I made such a mess of explaining something very easy. Quantum theory must be the integral of Z of the original thing over BG. Actually, when you get into categorical language, there are two ways to interpret that which are related but don't necessarily agree. So that could mean it could be the co-limit or the limit. So having a G action on the object means you have a bundle on BG with fibers Z of that. So if the object was a vector bundle, it'd be clear what I meant. And you can take homology with coefficients in that, or cohomology. Yes. Yes. So that's right. So let's try again. So and has two possible interpretations. Sorry?
What do you mean by action of G on?
Well, for example, if it was a zero category, then there would be a vector space, and that would be a linear action on the vector space. But I'll explain what it means for G to act.
Right now, that's just an object. It's just an object in your category, right?
Yes.
So what do you mean
But it's an object in an N category. So it has a lot of internal structure.
what do you mean by action?
Why don't you let me get to examples? Okay, so the correct thing to say, I should have said that, but I would get a little bit too far there, is you have the action of G on the ambient category, and you want the fixed point of that, which is the same as choosing an equivariant object. But let me not write the most general thing now, because I'll explain exactly what this means. I just want to flag, there are two possible interpretations of this. And one is a co-limit. That's analogous to homology over BG with coefficients in something. And the other one is a limit. That's analogous to cohomology over BG put coefficients in something. And actually, it is the case that if you want to get a well-defined theory, this had better agree. So these need to agree. These need to agree if you want to have any hope. If you want to hope to define a TQFT. So I'm not claiming that the examples I write, the fixed points object will satisfy the test of dualizability here if you start with any random example. That's a bit related to your question, what it means for G to act on an object, I think. So when I make that precise in different examples, you want to check at the end that what I write as the co-limit as the limit satisfies the condition of the Coboris hypothesis, so it really generates a theory. There finite groups, I think it's a theorem, but I haven't checked that. I mean, compact Lie groups is the topological issues. So let me do examples and I'll see exactly what we mean. Examples. Right, so let's say, actually, okay. Let's say G is so let's talk about the n equals 1. So let's have one-dimensional DQFTs. And you could take a reasonable category, take values seen as a category of vector spaces or complexes. Vector spaces. In that case, the fully dualizability condition is finite dimensionality. And in that case, it's easy to write the theory. The theory assigns to, well, a point, a vector space V, a point with a positive orientation V, a point with negative orientation, a dual vector space, and you can sort of imagine what's assigned to every picture. So this is meant to be a bordis between the empty set and the minus point and the plus point. So that's V tensor V check, and that is the identity map, and the other would be a trace, the evaluation map or a trace map to C. So the empty set, of course, is the vector space C. So this is C mapping to this by the identity, and this is the evaluation map, and the invariant for a surface dimension of V. So what it means for G to act on a point, especially if G is a finite group, it means that V is a vector space with a G action, but the intrinsic definition is you take the trivial action of G on the category, or comp, and ask for fixed points. And the answer is our complexes or vector space with a G action, our G representations. And there's an abstract definition of a fixed point category. If you have a category C, what is the category CG? A fixed point category consists of objects in C together with an isomorphism for each G, an isomorphism from X. So, sorry. G acts, I should tell you that first. It acts trivially, but saying that it acts means that for every element of G, you get a functor Fg from C to itself, and you get a composition isomorphism, Fg composed with Fh alpha Gh to Fg times H, and this must satisfy an associativity condition. So that's a constraint. In this case, when I mean say the trivial action, I mean everything is the identity. But now even then, saying that you have a fixed points actually gives you data, because what you require for each object x and for each, x of object in the fixed point category consists of an object in the category together an isomorphism for each phi between x and fg of x, and you have the coherence conditions with the alpha gh, which you can write down, and morphisms are the morphisms in C which are compatible with the data. Okay, so that's what it means for G to act on the object X. You're specifying data, but which comes from the ambient category, from the action on the ambient category. You've made X G equivariant. I start with a trivial action. So if you start with a trivial action on vector complexes, then if you think about what that is the representation of G on X, on the vectors, because fg of X is a. It means every fg is identity, and this is the identity. Right? Then exactly right. And it means for every g, you need a linear endomorphism of the space, and they must compose according to the rule in G. Right? That's just. So that's how you can define the representation just from, well, nothing, I guess. Yeah. Incidentally, there are some exercises you can do that are amusing, and they'll come up in higher dimension. You can guess generalization once I write the basics. So let's call it the fact. Actions of G on vect, on the category vect, are classified by I should say linear everywhere. So all the categories will be linear, all the functors have to be linear, and so on. Are classified by H2 of BG with coefficients in. Now let me write O star here, but you can read C star for a finite group, which are also central extensions of G by O star. And the cycle of the extension goes into the associator. And if you take the fixed points for a non-trivial action corresponding to central extension, you get the projective representations of G for that co-cycle. So this story extends. And actually that's true for any reasonable definition of higher categories. We'll find that the actions of G on a trivial object are classified by Hn of BG with coefficient O star, where maybe let me write n plus 1 if so actions on the unit in the linear linear, maybe that's n actually, linear n categories. Unit object. So that will be an n-1 category. Vect is a 1 category, have H2. That would actually be true. You have to define this, and there are, in fact, several possible definitions here. But any reasonable one should produce that. One easy way to say it is that an action on the line is a homomorphism from G into the units of a line. The units here are a line, so for every G, you want the homomorphism from G to pick the groupoid of lines. So for every element, you want the line LG, and they have to multiply coherently. So we have isomorphism LG tensor LH, LGH. And of course, all the lines are the lines of the central extension on G. All right. It's a tensor category, but I haven't used that to say that. I've only used it for a particular I've only used it for a particular argument for this statement, but in order to define a G action on vect, I just used the linear structure. When G acts on a vector as a tensor category, actually, the 2 will become a 3. So vect, you could say vect is a unit object inside linear to the last one. Unit object, I should say. That's a meaning. In linear category. So vect is the unit, like inside linear 2 categories. It's the simplest linear 2 category. Well, that's a bad way of saying it. Vect is the simplest linear 2 category, but perhaps it's a unit for a monoidal structure there. It's also that you could say that a linear category is, depending on your definition, is the same as a vect module. Oh, linear actions of G on this are classified by this group. Okay. And depending on this group is, we'll see that there are examples where a continuous family, so you can have a deformation theory of representations. Not quite for the compact groups on vect, but for something closely related. Right, so I was going to gauge a theory for a finite group. So you need, to assign to a point an invariant object, so a representation of this. So the gauge theory, it will be assigned to a point. Classically, you would want to assign, so you need a representation of G, and classically for a point with a principal G bundle, you assign the associated vector bundle over a point. Of course, there's nothing to see there, but so classically, so point and principal bundle goes to the associated vector bundle. Now, for an interval, there is something to see because, of course, if you have a principal bundle at each end, you can extend it to a principal bundle in the interval in many ways. In fact, just choose an element of G here. And here you had V, here you had V. And this is meant to be a linear map from V to V, which, guess what, is just the action of G. So this interval corresponds by the TQFT to phi G from V to V. This decorated interval. The decorated interval is principal bundle trivialized at the ends, or relative to the ends. And quantizing the theory means integrating over BG, which in this case, if you have a finite group and characteristic 0, means only one reasonable thing, which is if you have numbers, you have to average over G. And if you have vector space, you have to take invariance or co-invariance, and they be the same thing. So the quantum theory the point to assign the invariance, which is isomorphic to V sub G. And to the interval, you have to assign, put all possible principal G bundles and add up. So it's going to be the sum over all holonomies divided by the order of G of trace of the corresponding holonomy, trace V of G. And miraculously enough, if I got it right, it's the same as the VG. So in other words, the two ways of computing the invariant of the circle by summing up over bundles, or by seeing what's assigned to a point and then taking the dimension, give the same answer. So this is computation by summing over bundle. by integrating, say, bundles, and this is computation from Gobord's hypothesis, a bit pretentious, from Gobord's hypothesis. Right, because what you assign to a point in that case has to be the integral over Bg of V. The only interpretation is the invariant part. Incidentally, there are two ways to arrive at that. So now, if we take a Lie group, there are two possibilities we could look at. So, and it's going to have to do with what we mean by integration over Bg. So literally, if you ask for G actions, let's make it compact. G actions on vect, just as before, you get representations of G, and it's reasonable to ask for them to be smooth or continuous. So at that point, already you need to put a bit of structure so that the blind categorical recipe of fixed point gives you a continuous representation. But let's just believe that. Let's just believe we've done that. And if you have a representation of G, you're left wondering what. So if V is in there, you get vector bundle over Bg. So you're left wondering what it means to integrate over Bg V. And there is an interpretation of that, for example, in algebraic geometry, we interpret as cohomology of Bg with coefficients in V, and actually would pick up exactly the invariance, the homology would pick out the co-invariance, and you could show that they're actually isomorphic in characteristic 0 for a compact Lie group. And actually, we can repeat this story. In that case, the sum becomes an integral, and again, it's a known formula. But there's something else you could be looking at here, which is closer topology, in which this integration resembles something more topological. So, it looks strange at first. The only good motivation is that it actually comes up. And these are infinitesimally trivial actions. Or trivialized. Which are also, you could think of them as actions of the group, not the Lie group G, but the quotient of G by the subgroup G hat. G hat is a formal group at 1. And formally, it's a normal subgroup. So this is a group stack. Okay. So if G is connected, and you act on vector spaces, then of course infinitesimally trivial implies trivial. So on vect, G mod G hat actions are trivial. But on complexes, that's not the case. On complexes, the correct thing to require for a fixed point for this action is that G acts on the complex, and the Lie algebra action, or G hat action, has been homotopy trivialized. And that means that, well, so the complex has a differential. You have on each C, you have for every C in the Lie algebra, you have the infinitesimal action. And the homotopy trivialization tells you that for each C, you have an I of C degree lowering map satisfying the homotopy triviality relation. The I of C commutator is the Lie action of C. And actually, you need something a bit stronger. You need this assignment to be, so C to I of C to be invariant under the group, and you need I of C squared to be 0. If you have such a thing, then this gives you an object. So C becomes an object. Let's say a coefficient system for cohomology of BG. So it becomes an object in the derived category of local systems, in the derived category of equivariant local systems over a point. So the cohomology of BG with coefficients in C makes sense, as is does the homology defined. If you dualize one of these, then these two will be dual, have the usual relations. Unfortunately, usually these guys will not be finite dimensional. For example, if you really take everything to be trivial, just C, you get the cohomology of BG, which is not finite dimensional. So not finite dimensional, not usually finite dimensional. So even though you tried your best, you didn't quite get a TQFT. I mean, you'd like to say at one point you associate this guy to the plus point, and to my minus point you associate that, but if you ask what goes for the circle, it'll be something like the Euler characteristic, which is infinite. So it's not quite a TQFT, usually. I suppose I should say where this condition comes from. So if G acts on X smoothly, so X is a smooth manifold, and C is just a de Rham complex of X, then you get exactly this. And that ends up being finite dimensional essentially if the action is free or almost free. So pretty rare. So okay, let's move up to something slightly non-trivial as a two-dimensional situation. So actions, we have to look at actions of groups on categories. Actions and infinitesimally trivial actions of groups on categories, on linear categories. And here already things begin to branch a bit, but there's still a beautiful story that's self-contained. I'll tell you at least that. But so first, what's an action? Well, what's a category? Well, we know that, but examples of category. So C, let it be the category of A modules, where A is some algebra. I'm always going to write that, even though it's not a necessary assumption. With a bit of work, you can take almost everything for algebras and write within their categories, but I'll save myself some trouble. So now we have to if you think of A modules, so an object in G must give a functor fg from A modules to A modules. There are very nice functors which are associated to bimodules, tensoring over A with A bimodule. Should do it on this side. So X goes to mg tensor over A with X, where mg is an AA bimodule. And in fact, all colimit preserving functors are of this form. Like this. If we have an ordinary algebra automorphism, you get a bimodule simply by taking A, with the left action being the normal one and the right action being twisted by G. It's an example. All right. So the question is, what is the category of G fixed points in A modules? What is A mod G fixed point? And as you see from here, once you get to categories B, you might want to start imposing conditions like something is finite, what kind of modules, how is the action, continuous, algebraic, or so on. So I mean, that's some decisions to be made in every example. But in general, I mean, with some interpretation, this always has a uniform answer, which is that these are modules over some algebra, modules over the cross product algebra, G cross product A, where these are sections. These have to be interpreted very carefully. So these are sections over G of the bundle of bimodules defining the actions. The G action. So for each G, you have a bimodule and G. So you must assume that they assembled a nice bundle over G, bundle of A bimodules, and the action condition implies that the sections form an algebra under convolution, because you, as part of the action condition, you are required to have isomorphism of this form. So specified as part of the action. So it could be that, let's say if G is finite, it could be that all the bimodules come from an actual automorphism, in which case that's the usual group algebra, meaning sums of elements of G with coefficients in A and an obvious multiplication. But it could be that they're interesting. It could be that the MGs are line bundles over spec A, for example. We'll see an example like that. So what's an infinitesimally trivial action now? Well, the action. Then we have to begin to look at some homological algebra controls actions and infinitesimal automorphism of an algebra. And that, of course, is captured by the Hochschild complex. We work for a category 2. So what we want, so we have G acts as above on the algebra A. What we want is that the infinitesimal action is by derivations, by correctly interpreted derivation. So that's got to be a map, a linear map from G to Hochschild co-cycles of A. This form a Lie algebra under the Gerstenhaber bracket. So this is a Lie algebra map. And you want the action to be trivialized in the Hochschild complex, the Hochschild co-boundary from Hochschild co-chains on A. And you want to have another copy of G here in degree -1. Here the identity map. And you want, so let's call it L, and it's a Lie algebra map. You want this to be iota. And what you want to require is that this whole thing, L comma iota, this should be a DGLA map. From this trivial looking DGLA, what is quasi-isomorphic trivial DGLA, so -1, 0, to this little piece of the Hochschild complex. That's an infinitesimally trivialized action. In particular, if A is graded or differentially graded, then of course this looks like zero cochains as a total degree, so it could be a complicated thing. So there are constraints here even for a circle. So, example, so G is R. You need this guy which kills the action. Okay, actually, let's even decide L is 0. All right. Then iota has to be a Hochschild cocycle, but it must have Gerstenhaber square 0. In the complex. So in particular, for those who know about that, implies that T times iota, so L psi is a single basis element. The psi defines a one parameter family of formal deformations. So infinitesimally trivial action of the circle is an example of that is a one parameter family, a linear one parameter family of formal deformations of A. So bracket squares the unobstructedness condition. And here's, I'm running a bit out of time, so I can't explain everything, but here's something cute here. So the claim is that the homotopy fixed point set, the homotopy fixed point, homotopy because that's because homological algebra, fixed point category for such an action, for this action on A is equal to the category of modules over deformation, the formal deformation family. So over A bracket bracket H bar deformed, the deformation family. So let me explain that a bit. I'll write a general one. Given this, I want to tell you what the fixed point algebra or fixed point category of modules is. So there are two models for how. Actually, before that, let me give you an interesting example of infinitesimally trivial action. Example: G is a torus T, and let's assume that it's so trivial that really you can trivialize the action on the Lie algebra. So assume the stronger condition that the action has been trivialized. On the X of T, so on the universal cover of the torus. Okay. So this map has kernel pi, which is pi 1 of T. So now, at the point of pi of the kernel, we have now two trivializations of the action. One because pi maps to T, the identity in T, and that was the identity functor. And the other one because I've been trivialized up here, pi sits in T. So what you get, the difference between two trivializations, or the ratio of them, is an automorphism of the identity of the category. So we get, in fact, not just get, that's the same thing as a group homomorphism from pi to aught of the identity on your category C, a module, or if you prefer, algebra map from the group ring of pi to the endomorphism of the identity, which is the Hochschild cohomology of C, which is the same as saying that, well, spec of this guy, notice, probably the only Langlands duality that will appear today, is a dual torus. Check. So what it means, giving such an action is the same as fibering C over T check. You can tensor objects in C with coherent sheaves on T check, for example. So C becomes a module category over coherent sheaves on this check. So in particular, coherent sheaves on T check itself should carry a T action. What's the action of T on coherent sheaves on T check? And the answer is a Poincaré bundle. On T cross T check. So for each point T, you get a line bundle over T check. The assignment is multiplicative. And when you go to universal cover, you can trivialize the Poincaré bundle. You can write the quotient of a trivial bundle for T in T, PT, and PT tensor PT prime. Isomorphic to PT. Incidentally, this happens whenever you have the action of who, where? No, T. So for every point of T, you need a functor from this. That's a bimodule over this algebra, right? Oh, yes. I'm sorry. Yeah, right. So that's a bimodule over the algebra. You're quite right, yeah. So it's a modules over the functions on T check. That's right.
This idea about bimodule is just an example, right? Induction doesn't have to be.
No, the action on algebra has to be if you're in the two category of algebras, bimodules and intertwiners, and that's kind of the only reasonable thing to say. If you want functors within the category of modules and you want them to preserve colimits, they have to come from tensoring the bimodule. So, but you're right. If you don't ask that it commutes with colimits, there are more linear functors. So, I mean, it's easy to make general statements, but when you actually go to compute, you find you need more and more assumption depending on your categorical level for the obvious things to be true. So the reason this example is relevant is that in symplectic geometry, if T acts in Hamiltonian manner, on X, then you get a T mod X T action on the Foucault category, which tells you the Foucault category maps to the dual torus, and in fact, typically, essentially all toric examples and other examples, when people construct a mirror, they construct a mirror X check together with a holomorphic map to T check, and they study the action of T check that way. And incidentally, in this picture, by reaching ahead, let me tell you the fixed point category. So claim C fixed under T mod X of T, I guess, is a fiber over 1 in T check. So now what's a fiber over 1? Fiber over 1 will be home over the tensor category Koch T check of vect at 1 into C. So of course can also study home over coherent T check over tensor category of vect at some other point into the category C, where tau is some other point in T check. So what does that mean? Well, what it means is that there is another representation of T mod X of T. In fact, I'll give it an exercise now, that the actions of T mod X T on vect are classified are classified by exactly points of T check. Points of T check. It's going to be a long exact sequence that computes the cohomology. On the other hand, if you allow to preserve a degree, if you don't require to preserve a degree on vectors, you act on complexes, you can do a lot more stuff. So let me go on another fact. So actions of T mod XT on comp or graded vector space even vect are going to be classified by T check cross sim greater than 1 of the Lie algebra, of functions on the Lie algebra. So this would be sim 1. And this also parameterized deformations of the category vect as module over the tensor category of coherent sheaves on T check. That's reaching a little bit into the tensor category and the deformation theory. But I don't have time for that, so I will just explain to you in general.
So you explain what the classification of H is.
You have to compute H. Where are we now? H2 of B of T mod T check. That will be good enough. But you put exp of T with coefficients in O star. That we have to compute. So that is B2 pi with coefficients in C star. So that is just a topological space BT H2 of B of T with coefficients in C star. We're looking at H2 of BT with coefficients in C star. And there's an exponential sequence because there's no torsion in this guy. Next guy is 0 anyway. So this is going to be T check. And that is going to be phi check, a dual lattice, a dual of the lattice. So that ends up being T check. Then you have to look at B of G mod G check, and we can compute that too, but maybe I won't do it now. G hat, sorry. We're not at Langlands yet, yeah, sorry. That's the only shadow of Langlands at this point. I think it's not expected to appear in dimension 2 at all, anyway, so in 3. Vect is a module category over the coherent sheaves over T check, where they act simply by, so you can identify the category of skyscraper sheaves at 1. So vect 1 is Koch T check module by a sheaf here acting on, just have to tell you how it acts on C. Exactly, it's the derived fiber at 1, right? F tensor left derived over T check. That's a trivial action of, in fact, of T mod XT, not just of T. Exactly. Oh, if you take the fiber at 1, that's a good point. It's a fixed point category, so what you're computing are, what you want to compute is X over Koch T check tensor, vect 1, and let's go vect tau and vect 1. And you won't be surprised to find out it's 0 if tau is not 1. Tau is not 1. So it doesn't see that there are no maps between different isotypical components, so to speak. And what you get at 1 is going to be sim T check. And this is in degree 2. Sim T check modules. Vect 1 to vect 1, yeah. If tau equals 1. So the tensor, it's the home of two module categories over a tensor category. The answer is a module it's a category and the category of modules over this algebra. And you notice a degree shift compared to doing X over T check of C, a skyscraper sheaf at 1, which will give you lambda tau check, lambda T check. Degree 1, and this is degree 2. So the formation theory of this skyscraper sheet, categorically the skyscraper sheet, is controlled by symmetric algebra. There is a looks a bit like causal duality, and you brought it up. Sorry, I'm out of time by 2 minutes, but I would like to write the model for a general Lie group for what a fixed point category is. Can I take 3 minutes? I'd like to take two models and with a causal dual to each other. So the fixed point categories would be categories of modules. Over an algebra. And of course, in this categorical world, as I said, you have to start making assumptions somewhere. What kind of finiteness, what kind of modules, and so on. And the definition, what you get are equivalents of categories modulo finiteness conditions, which you have to decide what you impose. So there are two models, and one is better than the other. There's the obvious model, which is essentially the cross product G mod G hat with A. And by this I mean that you are going to take the de Rham complex, actually, let's take it properly, C infinity of functions on the group with values in the Lie algebra, and the differential being the Lie algebra differential. So that divides out by the formal group, tensor in a twisted way with A, and have enough info to make that into an algebra. So for example, if you have a Lie algebra element from here, you have to impose the commutator with some element of A has to be that contraction. Psi, just I have psi applied to it. That's where you use the contraction information. The group action actually used by acting. If you didn't have that, you would know what I meant by this. It would be the cross product algebra. That's the obvious model. And there's a causal dual model, which is more familiar. And that's it will look very much like Cartan complex. It's a cross product of G with algebra A, tensor sim G star. I've used checks for dual, maybe? Okay, well, maybe not star. Sim G star. And the differential is going to be the usual equivariant differential, so differential on A plus psi IA. And there is a twist here in the form of a potential, which has the form psi of 1 tensor psi A. It's a quadratic thing, where this guy is a linear function on G, and this is a derivative of a delta function on the group. So it's a distribution on this fellow. And this is a curved algebra and has a DG category of modules. A well-defined differential graded category of modules. And that's a fixed point category. And the last thing I want to add is you can begin to have fun now. So we've said that you can deform the action on vect by things in, so can deform on vect by sim G star G invariant classes. And they appear here as potentials, or curvatures, sorry. Curvatures I won't have to explain, which are Landau-Ginzburg potentials. And the most important invariant here is the quadratic form. So this contains the quadratic summation of psi A, psi A. So invariant quadratic form. And let's give it a name, H. And the little theorem is that adding H semi-simplifies the category of modules modules and and makes it equivalent to the category of representations of the group. And I won't explain the last bit, but there is an analog for loop groups. And loop groups, I mean, as a story in development, are related to, or have some connection with G actions on tensor categories. I can talk about that some other time. So I didn't get to 3 categories, sorry about that. But no, 2 categories, 3 I was never going to get to. But, what's the point of all this? So I think the point is the one at the beginning, that you want to understand how to generate higher dimensional gauge theories as TQFTs. And I think the simplest ones are gauge vect. I mean, try to look at representations of the trivial action of G on vect as a tensor category of higher and higher order and ask, what's the fixed point category? Does it generate TQFT? Do we have to modify it in some way? So for example, in this case, just take the naive thing, it doesn't. You get something like a cohomology of BG in dimensional space. But if you start adding potentials, it does. You actually get, I should have said this topological Yang-Mills theory in dimension 2. So it's well, I explained it for the torus. I didn't explain it for G, but I'll let you do the calculation. It looks very much the same. You have to allow all of this, all even cohomology. So these actions are not so much on vect, but on complexes or graded vector space, and they're no degree preserving somehow. So we're adding H. So H is an element here. This is a space of functions on the Lie algebra, and they can be viewed as curvatures in the sense of curved algebra. Curved algebras, or Landau-Ginzburg potentials. They're potentials for this algebra. You already have one anyway in this model. It's already a curved algebra. So at that point, you can ask, well, how can you change the curvature? The square is a commutator. But there's a well-defined DG category of modules of such a thing. So the fixed point category is defined and represented as a category of modules of a curved algebra. It's not a 2-dimensional TQFT in this case. So vect G or G check does not generate something sensible. Yes. But the simplest deformation that you have, which is what a quadratic potential does, and it's something well known, it's Yang-Mills in dimension 2. Deforming the representation on vect, or adding it as a potential in this particular model. So the theorem is that when you deform the representation, compute the fixed points of a deformed representation, you compute them by the curved algebra. That's right, yeah. That's right. So vect deformed. Yes. That already, in this case, it is. We know what it is, in fact. Yes. Yes. The loop group and the loop group analog. I mean, you are going to get a K-theory version of that and its deformations. So you. No, it's still 3-dimensional. That will be, so this is 2-dimensional. Loop groups would have something to do with 3 dimensions. So that's where I kind of stopped. I didn't get to 4 yet, but computations get difficult.